The next two fields I want to focus on are the sequence and acknowledgement number fields, and you'll see those in the second and third rows at TCP4 and TCP8. And these are important fields because they're really probably the two most important fields that allow TCP to be concerned with reliable delivery of information and making sure data is getting to where you want it to get to. Now, it works through a sequence of numbers that are transferred between the sender and the receiver. And very simply, the sender sends a specific number that's based upon the amount of data it's sending, and the receiver adds that iteratively as it goes along and sends the next expected number back to the initial sender. And what that allows us to do is look for packets that are either dropped or out of sequence. And that may seem a little odd in your head when I say it just like that, but don't worry, we're going to go through a couple of examples, one theoretical and one actually within some packets, so you can actually see this in action. So if it doesn't make sense quite yet, don't worry, we're going to go through those examples. Now, again, two fields are a part of this: sequence number and acknowledgement number. Sequence number, very simply, is used to identify a TCP segment. And when I say segment, I'm referring to the TCP header within the packet. That's the proper term. I'll still use TCP packet interchangeably, but when I say segment, that's the proper way to refer to just that TCP header within the encapsulated packet. So the sequence number is used to identify the TCP segment and ensure parts of the stream aren't missing. And the acknowledgement number is basically the sequence number that is to be expected in the next packet from the other device in the conversation. So that's what we're talking about when we talk about sequence and acknowledgement numbers. And it's important to know these are just numerical fields. They can be very large numbers since they're 4-byte fields, but they are just numerical values that are iterated on as the communication between two hosts progresses. The important formula I want you to remember when thinking about sequence and acknowledgement numbers is this one. And this is from the perspective of the recipient or the server in that case. And the formula is sequence number in plus bytes of data received equals acknowledgement number out. So let's walk through a theoretical example of what I'm talking about here using the graphic that's on the screen now. In this case, we have a transmitting host and a recipient host. You can think of these as the initial source and destination or client server, but for our purposes, I'm going to refer to them as the transmitting host, which is initiating the connection, and the recipient host, which is receiving and responding to the initial connection request. Now, in this case, we're transferring TCP packets back and forth. And now, we haven't talked about this yet, but TCP has a handshake process. Every TCP connection must begin with this handshake process to exchange vital information needed for ensuring the reliable delivery of data. We'll go through that specific process later on. What you need to know now is that during that handshake process, a piece of information is exchanged called the ISN, or initial sequence number. And that's a number chosen by the transmitting host, which is basically just a starting point. And that's just saying, I'm going to start with this sequence number. So you see in the first packet, which is this first arrow listed here, sequence number 5000. That's the initial sequence number. We also see data size 500. Well, why is data size 500 important? Well, that's because we add it to that initial sequence number that's coming in, and that's the acknowledgement number that is sent back to the transmitting host. So with TCP, anytime data is received by a recipient, it has to acknowledge that data coming back. Now, that's not always a one-to-one acknowledgement. There's this concept of selective acknowledgement we'll talk about in a little bit, but to some degree, data has to be acknowledged. And that's when that's done, when a recipient acknowledges that data was received, it sends a TCP segment, a TCP packet back to the transmitting host without any data, just a TCP control packet, and that has an acknowledgement number. And that acknowledgement number is the previous sequence number plus the number of bytes of data received. So in this case, the initial sequence number was 5000. The data size was 500. You add those up, that's 5500. The recipient host sends an acknowledgement packet back with an ACK number of 5500. And that now is the sequence number that the transmitting host is going to use to send the next packet. So you see the next packet, the third arrow in this line, is sequence number 5500. I send another 500 bytes, and the recipient sends back 6000. It's adding 5500 to 500, and it's acknowledging with 6000. This happens one more time. The sequence number at that point is 6000. The transmitting host sends 500 bytes one last time, and the recipient host responds by adding those together, and the acknowledgement number is 6500. What's being done here is the recipient host is basically telling the transmitting host what the next expected sequence number is. And this is so important because what this allows both the transmitting and recipient host to do is to find packets that were dropped or were not received. If the recipient host receives a sequence number that's lower or higher than what it's expecting, it knows something's wrong. If the transmitting host misses an acknowledgement or receives an acknowledgement that's lower than expected, it knows that the recipient didn't necessarily receive a packet that it was supposed to receive. So there's this concept of both the transmitter and the recipient are taking responsibility in determining if packets were lost in a communication sequence, and that's pretty darn cool. I'm going to go through some troubleshooting exercises later on in the later section. We talk about latency to show examples of what happens when segments are dropped. We'll talk about things like duplicate acts and fast retransmissions and things like that, and that'll be pretty neat. But for now, just understand this is the basics of how sequence and acknowledgement numbers work within the scope of the TCP header. I flipped over to Wireshark now because I want to show you an example of TCP sequence and acknowledgement numbers in practice. And we haven't looked at any other TCP packet captures in depth, at least that header in depth yet. So you're going to see some things you don't understand quite yet, and that's fine. We're going to be learning more about these iteratively as we go through this section. But I do want to show this sequence and acknowledgement number kind of dance that goes on between the transmitter and the recipient of the connection, or in this case, the initial source and the destination. So I've gone ahead and opened up http:/google.pcap, which is just a user from a browser connecting out to Google to download the homepage. So it's a pretty simple capture, but it's an HTTP transaction which relies upon TCP, and that serves our purposes here. So before we get started, I want to show something kind of interesting. Of course, if you look over here in the right-hand column of the info area, you see for our TCP packets, you see a sequence number listed here, and here below you see acknowledgement number. You also see these sends and syntax and things like that, these TCP flags that we're going to talk about a little bit more in depth here in just a moment. For TCP control packets, which are TCP packets that don't actually have any data embedded with them, you'll see the relevant TCP data in the info column. However, when you have application layer protocols doing things, in this case we have an HTTP GET request in packet 4, you're going to see the higher layer protocol information. So in this packet, if I click it, you'll see there's actually a TCP header in here with a lot of information, but Wireshark chooses to show the highest layer packet information instead. So instead it's showing this HTTP information instead of the TCP information. So that's an important note when thinking about how Wireshark shows information by default in relation to how packets are encapsulated. Now, if I go back here to the first packet and we have the TCP header expanded, notice if I click on the TCP header, down here at the bottom where we highlight, there's nothing after it. So this is a TCP control packet, and we say that because it's transmitting, it's helping set up the TCP session. It's a function of TCP and the features it provides, and it doesn't actually transmit any data. And there's quite a few instances where this is occurring, and we'll go through those. But in this case, it's just a TCP control packet, and so we have just this header, and we'll see we have the sequence and acknowledgement numbers here. As a matter of fact, here's a sequence number set to 0, here's an acknowledgement number set to 0. Now, that's kind of weird, right? We talked about the initial sequence number, and that one of the things the source should do, or the transmitter should do, should set up and provide an initial sequence number when it sets up a new connection. And in this case, the sequence number is 0, but that's not quite right. That number should not be 0. It's not going to be 0 for every communication going on with your host, of course. It has to be a little bit variable. So the reason we see zeros here is because of what we see in parentheses, relative sequence number. Wireshark is trying to make it easier for us to analyze these sequence acknowledgement numbers by setting them relative to 0 at the start of this conversation. And that's a pretty darn cool feature, but I actually want to turn it off now because I want you to be able to see these sequence acknowledgement numbers for what they actually are, at least in this case. Now to do that, that's a protocol-specific setting. So we're going to go up here to Edit, Preferences, go into Protocols. I'm just going to type TCP to get down to that section. And you'll see we have this option for relative sequence numbers, which is enabled by default. I'm going to go ahead and uncheck that and hit OK. And immediately you'll notice that our sequence and acknowledgement numbers have changed. Our acknowledgement number is still 0. There's no value for that, but our sequence number now is much larger. 2082 691767. So we have the actual proper sequence number, which is what's actually transmitted in the packet. And if I click on that and highlight it, which is what I've done now, you see down below in the packet bytes window that that number is actually highlighted. In this case, it's hexadecimal 7C235AB7. But in this case, that's the sequence number, or the initial sequence number transmitted by our source host, which is 172.16.16.128. Now in this case, we see what our initial sequence number is, and we see we have an acknowledgement number of 0, which is what is to be expected on the first packet in this connection. Now if I scroll down to the second packet, you'll see we actually have sequence numbers and acknowledgement numbers both. Now there's a sequence number here because we have two-way communication, right? So the recipient is actually sending its own sequence number, but what we're going to be concerned with is the acknowledgement. So if you look here, our acknowledgement number ends in 1768. If we go back one, our sequence number is 1767. So remember our formula that it's bytes in, its initial sequence number plus bytes in equals acknowledgement number out. Now in this case, remember this is a TCP control packet, so there actually isn't any data payload, but a sequence number has to increment. So even when there's not a data payload, the sequence number will increment by 1, at least in the TCP handshake, which is what we have here. Again, not something we've talked about quite yet, but all TCP connections are set up with an initial handshake, which consists of 3 packets: SYN, SYNAC, ACK. So we have the SYN going to the recipient, SYNAC going back to the transmitter, and then ACK back to the recipient before normal communication begins, which begins in packet 4 with our GET request. So in this case, again, we have initial sequence number ending in 1767. There's actually no data being sent, but since we have to increment it, it's incremented by 1, and we have 1768 as our acknowledgement number being sent back. Now remember, the acknowledgement number being sent back is basically the recipient telling the transmitter, here's what I expect the next sequence number to be. So if I click on this third packet, we should see that acknowledgement number, this 1768, should be our new sequence number. Sure enough, it is 1768. That's the last 4 digits in this case. So that's what we have going on there, is we have that acknowledgement now becoming the sequence number. Now let's move on to where we actually have data being transmitted, and we'll actually look at this HTTP GET request. Remember, Wireshark is showing us in the info column the application layer data, the HTTP data, instead of the TCP data. We can see here we still have a TCP header to work with that's responsible for this communication. Now in this case, notice our sequence number. In this case, it's 208.269.1768. We'll just focus on the last 4 digits of that because that's relevant for us. Now in this case, we actually have real data being transmitted. If I click on the TCP header, you see there's data after it. That's responsible, the HTTP protocol is responsible for that. You see that highlighted there. So we have actual data being transmitted here. So we know that basically our recipient should take the sequence number we provide, which in this case is this one ending in 1768, add the amount of data being transferred, and that should be our next, that should be the acknowledgement number it sends over, therefore our next sequence number. And notice Wireshark actually helps us out a little bit here. It actually pre-calculates this information for us. You noticed when we looked at the TCP settings earlier, there was an option for Wireshark to do sequence number analysis, and that's a feature it provides where it just makes this a little easier. So this means we don't have to click onto the next packet to look at the acknowledgement number. The acknowledgement number is going to be this right here, this value ending in 2395. For posterity's sake, we'll go ahead and click over to that, and you'll see that that's exactly what the acknowledgement number is. It ends in 2395. So I'll go back to this packet because we can see both of them at once. We have 1768 and 2395. So ideally, we should take 2395, subtract 1768, and that should be the amount of data being transferred in this packet. Now, that makes sense, but let's go ahead and actually do the math on that because I want to show you something that's pretty important here. So I'm going to go ahead and run calc.exe, and you might expect me to be able to do this this math in my head, but I'm not even close to that good. So we'll go ahead and run calc.exe. Let's go ahead and move it over to the side here. I will take 2395, subtract 1768, which are the last 4 digits of those sequence numbers and acknowledgement numbers. Those are the only things that are changing. And we see we have a value of 627 bytes of data. Now, if I go back to my Wireshark window and look at length, I see 681 bytes. That doesn't match up, right? That's not 627. So what am I missing? Well, remember, this length column that I created, it's actually created from the IP header. So it's the total packet length. It's not actually the length of the TCP segment data, which is actually what this is based on. The TCP data, TCP layer is not aware of the IP layer in that way, or not aware of the entire packet size. Now, if you look over here, you look above, you see we have TCP segment length 627. That's actually what we're concerned about here. So if I want, I can actually go ahead and right click that, and apply that as a column. And we can see the difference between the total packet length and TCP segment length here. So you can kind of get a sense of what's going on with the data being added. Remember, the important part to keep in mind here, just to understand and grasp sequence and acknowledgement numbers, is that from the standpoint of the recipient of the server, whatever the non-initiator of the communication is you have a sequence number in, you add the number of bytes transmitted, that equals your acknowledgement number out, and that acknowledgement number out becomes the next sequence number you should expect from the sender or the person who initiated the communication. So pretty straightforward once you kind of see it in action, I hope. Now I'm going to go ahead and go in here to preferences and go ahead and change to turn TCP relative sequence numbers back on. I actually like this feature. I wanted to show this demonstration without it first, but I do like the fact that it uses smaller numbers because those are a little easier to process than those much larger numbers. We still have the things we would expect. We have TCP segment length at 627 here. In this case, that makes our next sequence number 628 because remember our sequence number was 1, speaking relatively at least. And so that just makes it a little bit easier to keep track of those sequence numbers if you need to for whatever reason. Now, real quickly, before we leave sequence and acknowledgement numbers behind for the time being, I do want to show you what that looks like in T-Shark. So here I'm going to go ahead and run tshark-r for the same file we looked at, http google.pcap. I'm going to say C5 just to show me the first 5 packets, and you'll get a Wireshark we've come to know from T-Shark, an output we come to expect from that. And in this case, we have our send, SYNAC, ACK, and we see some initial data transmitted. Of course, just like in Wireshark, with the info column, we can see sequence numbers and acknowledgement numbers where they exist. Of course, T-Shark's going to default to showing those as relative sequence acknowledgement numbers, which I'm fine with for now. But of course, in packet 4, we can't see that information. And you may not necessarily want to output all of the packet details for all of these because it's just way too much information to scroll through. But there is another option here. So I'm going to take the same command we just used and do -O TCP. And what that's going to do, it's going to tell T-Shark to only output the information for each packet related to the TCP protocol. So only output the TCP details information. So I'll run that, and you'll see that all 5 packets are output here with just that relevant information here. So in this case, you see we have the summary lines for the frame information, the data link layer, IP layer. We also have the summary lines now for the TCP information, and that's what we really want. So here we can actually look down this list and see this list of sequence and acknowledgement numbers and do sequence and acknowledgement analysis as we need to. So this is just another way to view the data. It's probably not a way that you're going to use a whole lot, but if you do want to view information this way and just view kind of that collapsed version of the packet detail view, this is a pretty cool way to do it, and that -O option is going to allow you to do that and to view that information in that way.